Hello, this is Graham Neubig, and welcome back to CS 11747, Neural Networks for NLP. This time I'll be talking about advanced search algorithms in the search problem. So the generation problem is essentially that we have a model of P of y given x, where y is usually a sentence if we're doing text generation or some other sort of structured object. And so how do we use this model of the conditional probability to generate a sentence? So there are essentially two methods that we've also talked about a little bit in previous classes. So first is sampling, where we try to generate a random sentence according to the probability distribution, and argmax, where we try to generate the sentence with the highest probability. So the question becomes which to use. And which to use is kind of motivated by the problems that we want to handle. So if we want the best possible single output, for example, because we're only going to show one output to a user, we might want to do search. If we want to observe multiple outputs according to the probability distribution to have a better idea of what the model kind of believes or what it thinks are the space and plausible outputs, we can do sampling to get some random samples and give us an idea about that. And sometimes we want to generate diverse outputs so that the model is not boring. And in this case, we can do that through either sampling or search. And I'll talk a little bit more about all of these in a second. So regarding sampling, especially if we want to do sampling to observe the underlying probability of a distribution, underlying features of a probability distribution, if we have a factored model, like a left-to-right model or any other autoregressive model that conditions output predictions on the previous output, the easiest way to do this is to randomly generate words one by one. So basically, we have our input, and we calculate the probability of the next word given the input in all of the previous words. And until we reach the end of sentence symbol, we just randomly sample a word according to this conditional probability. So this is an exact method for sampling a P of y given x, and because of this, no further work is needed. This is the best possible algorithm we can use for performing the sampling in an unbiased fashion according to the probability distribution. Notably, I talked about several reasons why you might want to do something like this, and so this is sufficient for the second reason why we would want to be doing some sort of generation. It may or may not be sufficient for the third reason, where we want to generate diverse outputs. So I'll talk a little bit more about that later. Another thing to note is any other sampling method is not an appropriate way of visualizing or understanding the underlying distribution. There are other sampling methods that could be used to generate outputs, but if we really want to know what the model knows or what the model thinks are the space and plausible outputs, then this is the only method and the best method that we could use. Now let's move on to search. So search is to solve the argmax problem, where we want to find the best output. And then the question becomes, what is the best output? And this is actually a tricky question, of course, because especially in open-ended generation problems, we might actually not know what this is. So the first way we could define the best output is the most accurate output. So we have some sort of reference or even human evaluation of the outputs, and we would want to generate an output that gives us the one with the minimum error, or the minimum difference between the reference and the generated output. However, of course, this is impossible a priori because we don't know the correct answer in advance, otherwise we would just output it. So we can't necessarily use this method in practice. So alternatively, the way we usually define the quote-unquote best output that we are searching for is the most probable output according to the model. So here, what this means is we define the conditional probability according to the model, and we find the output with the highest conditional probability. So this is, very standard. It's what we have used most of the time now. But notably, this is not necessarily tied to the accuracy because we have no guarantee that this conditional probability will be high in places where error is low. Another alternative search algorithm, these search criteria are actually also called decision rules within decision theory. Another alternative decision rule is we pick the output with the lowest Bayes risk. And basically what Bayes risk means is given the model probability of a whole bunch of outputs, we calculate the output that has the lowest expected error with respect to all of these models. So basically, with respect to all of these outputs. So basically what this means is, given what the model thinks are plausible outputs, which output would be the one that is the safest or the least likely to cause a major error? So this is good because now it combines the model probability together with our whatever concept of error that we have here. And in practice, one way you can do this is you can do this by outputting an n-best list or some sort of list of n outputs, calculating the probability of each of them, then calculating a matrix of errors between these two values, and then using that to calculate this expectation. So this is important to think about because many people don't necessarily think, during search, we're searching for the most probable, but what we actually want to use, what we actually want to output is the most accurate. So Bayes risk gives you a kind of thing that's in between those two. It's plausible to calculate, but also considers the error. So to reinforce this a little bit, we can think about search errors and model errors. So basically what search errors are is the failure to find the most probable output, or the failure to find a more probable output in favor of a less probable output. And this can be quantified by purely looking at the model score. And if there's any output that is better than the one you found, then this is a search error. So the search algorithm fails to find an output that optimizes its search criterion. In contrast, the model error is the output that optimizes the search criterion does not optimize accuracy. So in other words, this means that the model score, maybe the Bayes risk, are decorrelated with the actual accuracy of the model. So this is an example from one of my papers where we demonstrate this more saliently. So what you can see is on the top, we have the model score based on how much we search, essentially. This is the size of an n-best list that we generate, that we search over. And you can see that the model score, as we search over the n-best list, continues to go up, of course, because if we search more candidates, then we're more likely to find a high-scoring candidate. However, the blue score, which is our measure of model accuracy, does not necessarily go up monotonically. In fact, it goes up for a while, and then it drops for a little bit, and then it goes up, and then it kind of fluctuates. And these fluctuations basically are indicating model errors because the model score went up, but the accuracy went down. So this is a really, really important concept to be familiar with. And basically it means that we don't necessarily want the most likely output. So first I'm going to talk about searching for probable outputs. So I'm going to be talking about how to reduce search errors. And the first way to search for probable outputs, which we've already talked about in an early class, is greedy search. So one by one, we pick the single highest probability word. So basically we step through the input just like we did when we were doing ancestral sampling. But instead of sampling randomly from the probability distribution, we pick the argmax. So this gives us the highest probability output at each time step. However, it's important to know that this is not an exact search algorithm, and it can cause real problems in your outputs. So it will often generate the easy words first, or will prefer multiple common words to one rare word. So just to give a couple examples, if we have problems with disparate search difficulty, sometimes we need to cover specific content, some easy and some hard. So let's think of the problem of translation of a sentence like this. And we have, I saw the escarpment. And let's say I is pretty obvious how to translate it. We'll translate it into Japanese as watashi most of the time. Saw would be translated into mita most of the time. But the escarpment, there's many different ways to translate it, and also it's a low frequency word, so maybe our machine translation model hasn't seen very many examples like this, so it doesn't know whether it should be dangai, zeppeki, kyu, shamen, iwa, or some other word here. So basically what this results in is the translation of this word gets relatively high probability, the translation of this word gets relatively high probability, and then the translation of this word would split the probability over a whole bunch of examples. And greedy search, for example, can cause the search algorithm to select the easy thing first and then the hard thing later. So a conceived search algorithm essentially would generate this gold standard thing, like watashi wa dangai o mita. This is a correct translation of I saw the escarpment. However, an incorrect or not ideal search algorithm would do watashi wa mita or watashi ga mita dangai. So basically, it would output the words that are easy first because they would be favored by this kind of local argmax that we do over the words, and then once it's output this word once, it can't go back and revisit its decision because it's doing a greedy search where it is locked into the choices that it's previously made. So you might get a mistranslation where you get the word order incorrect, like watashi ga mita dangai, which means the escarpment I saw instead of I saw the escarpment. So this is one example. A second example is problems, for example, where you could express similar content in a single word or action or multiple words or actions. And just to give an example of this, let's say in a spoken dialogue system, it says, where are you from? And then the answer could be Pittsburgh or New York or New Jersey for whatever reason. The probability is split over all of these. And the score for Pittsburgh is 0.4. But the score for other one, New York and New Jersey, is 0.3 and 0.25. And basically what would happen is when we're trying to output the first word, the score of Pittsburgh would be 0.4, but the score for new would be 0.55 because New York and New Jersey would both contribute to the score for new. And this might result in new being locally optimal, even though this New York and New Jersey both are not finished outputting, so you would be paying a price later. So this is yet another example where basically the model has not made a locally bad decision, which can cause a globally bad result by using this greedy search algorithm. So one way to fix this is beam search, which we've also talked about a little bit before. But basically, beam search, instead of picking the highest probability or score, we maintain multiple paths. So at each time step, we expand each path and choose a subset of paths from the expanded set. So basically, this is an example here with a probability of A, B, or with a vocabulary of A and B and end of sentence. So the first time, let's say our beam size is 2, we would expand A and B and end of sentence. And we see that A and B are the highest scoring ones. So then for all of the remaining paths, so all of the all of the sequences that start with A and B, we would expand all of the following paths, like AA, AB, and A end of sentence, BA, BB, B, and end of sentence. And because our beam size is 2, again, we calculate the probability of all of these, and then we keep only the 2 highest scoring ones. So we get AB and BB, and then we further continue on. So this is a really relatively simple algorithm. It takes a little bit of work to implement, but it's pretty widely used here. So interestingly, this model, or this method for generating outputs is good, but it actually can make search errors in both directions. It still can't find the best. It still can't find the best output. So if our beam size is too small, like for example, if we used a beam size of 1 equivalent to greedy search, it would make a search error when it selected B here. It would have pruned out A, despite the fact that AB is the best sequence. It can also make search errors in the opposite direction. So it can find outputs that are worse scoring than the actual highest scoring output. So to take just a simple example, you see this empty string here actually gets a score of minus 1.39, but it gets pruned away because our beam size is 2 at the first step. In the final second best hypothesis it finds is minus 1.61. So it actually failed to find this minus 1.39 because it got pruned out too early, basically. And this is also an issue and can cause some problems that I will be talking about later. So anyway, going into basic pruning methods, how do we select the paths to keep explaining? So one way, or the most popular way, is called histogram pruning, or also fixed beam size pruning, if you want to call it a simple way. But basically what we do is we keep exactly k hypotheses at every time step. So in the previous example, we kept exactly 2 hypotheses, and we're doing a variety of histogram pruning. There's also score threshold pruning, which is keep all hypotheses where the score is within a threshold alpha of the best score S1. So what that would mean is, for example, we might choose a threshold of 1, and we would keep all scores that were no more than 1 worse than the best score that we have seen at this time step. And this can be useful because in some examples, or in some cases, we're very, very certain of the next output, and in some cases, we're not very certain of the next output. So basically what this does is it allows us to adaptively scale our search time based on the certainty of the number 1 output. So if the number 1 output is way more certain than the others, we just remove all of the other hypotheses. And if the number 1 is very close to the number 2, 3, 4, 5, 6, 7, 8, 9, 10, you would keep all 10 and continue searching there. Another option is probability mass pruning. So this keeps all hypotheses up until a probability mass alpha. So essentially, we want to keep all hypotheses that give us the sum of the conditional probabilities. I see the first 2 used more frequently than the last one, but this last one is another option. Another thing, a downside of score threshold pruning is that if the model really is very, very uncertain, you could get an absolutely huge number of hypotheses to prune. So very often it's common to do both score threshold pruning and histogram pruning, where you set a fairly large beam size k and then reduce it further with this alpha here. So another important concept, or another concept that is potentially very useful, but actually I see used a little bit less frequently in neural models, is something called a future cost. And basically what the future cost does is it tells you how much probability do I think I'm going to have to pay before I get to the end of the sentence or the end of the generation. And so normally what we do is we search based only on the log probability or the cost up until the current point. But in addition to this, we estimate the full cost to the end of the sentence and add these together to search. So if you're familiar with the A-star algorithm from an artificial intelligence class or machine learning class or something like this, it's a very similar idea. We have our current score, and then we have the heuristic function here, which estimates the remaining score that we're going to have to pay until we get to the end of the sentence. So Philip Cohn's book on machine translation has a good explanation of this. And Lee et al. 2017 talk about a way you can incorporate this into neural models, a paper called Learning to Decode for Future Success. So basically, you train a future network that basically just guesses how much more of a score you're going to have to pay to get to the end. And so the reason why this is good, if we go back to the concrete example, is let's say we have this hard example here, and the future network or the future cost function would know that translating this word is going to be very hard because it doesn't know how to do it. So basically, if we do watashi wa dangai and watashi ga mita, the future cost would know that it has already finished translating this kind of very hard word, and it would suddenly drop the future cost down to near zero. Whereas here, the future cost would remain high because it has not yet translated the difficult word. And because of this, the future cost would basically adjust for this fact and reduce the number of search errors that you may encounter in this way. So one other question that's an important question to ask, I think, is how large of a beam size would we need to do effective search in models? And I think basically the answer is it varies depending on the strength of your model and the difficulty of your search problem. So basically in search problems that are harder, with more uncertainty, you'll need a larger beam. In search problems that are easier with less uncertainty, you'll need a smaller beam. So one example of something with lots of uncertainty would be dialogue generation. One example of something with less uncertainty would be something like machine translation, because the semantics of the output are kind of fixed based on the input sentence. So that's an important thing to think about. So I'd also like to talk about search and problems with modeling. So one thing to note is that better search can hurt results, or can hurt results as measured with respect to accuracy metrics. So a very famous example is that better search or better model score can result in quite a bit significantly worse BLEU score in machine translation. So this dark green line here is basically the BLEU score of a machine translation model as you increase its beam size more and more and more. So why do you think something like this would happen? The answer is model errors. And more specifically, in this particular case, it's model errors with respect to the length of the outputs. So the better search results in shorter outputs. And I'll talk a little bit more about that in a second. But it's not the only reason why search errors could occur, of course. So how do we fix model errors? So let's say, let's go back a second, and let's say we encounter a phenomenon like this, where we're making our search better, but our accuracy, according to whatever accuracy metric we prefer, is getting worse. So how do we fix these model errors? And the best way to do so is basically to train the model to maximize accuracy or minimize risk. And this is the best way of doing things. And we covered a bunch of different ways to do this in previous lectures. So basically things like reinforcement learning, minimum risk training, structured search algorithms, et cetera, et cetera. So if you can do this, I would highly suggest you do it this way. This is the kind of like correct way of doing things. It's well principled, and it's you know, kind of guaranteed from an ML perspective to move you in the right direction. However, this can be hard in some cases because the machine learning, you know, algorithms that are used here can be unstable, like I mentioned before in the reinforcement learning part. So there are other options that you can use if you're not familiar, like if you're not willing to go that far. And another one is to change the decision rule to minimize risk. So again, like I talked about before, we have the Bayes risk decision rule that you could use to minimize the risk. And this is also well principled. It's guaranteed to lower your expected risk if you use it appropriately. Another way to do this is to heuristically modify the score post hoc, and I'll talk about a few ways we can do this in a second. This is kind of okay in my opinion. It's not the best way to do things, but it's rather convenient because you don't need to train your model. You don't really need to modify your search algorithm very much. And another way to do it is to hobble the search algorithm so it makes more search errors, but the kind of errors that you want. I'm not a huge fan of doing this because it can lead to kind of unpredictable results and entangle model improvements and search improvements, but it is a common strategy to be used, so I think it's worth knowing about it and thinking about the implications. Okay, so now I'd like to go a little bit more into minimum Bayes risk decoding. So the basic concept is we want the outputs that look safe given all the other high probability outputs, as I mentioned before. So to give a concrete example of this, let's say we have a dialogue system, again, that is trying to generate outputs. And it's asked the question, what is your name? And let's say it's a dialogue system impersonating me or something like this. And so then the first probability, and this actually happens quite frequently in dialogue systems. The highest probability thing is I don't know, because it appears a lot in the corpus. And then after that, we have my name is Graham, my name is Graham Neubig, my name is Neubig. And what you'll notice is that all of these hypotheses that use my name is are higher in aggregate probability than I don't know. However, they're not exactly the same. So if you pick the argmax with respect to probability, you would pick I don't know, which isn't a great answer. So minimum Bayes risk essentially tries to find these high scoring aggregate clusters, and it's operationalized as searching for a hypothesis that minimizes the risks. So in other words, like I said before, we have the error between all of the hypotheses and the probability of all of the hypotheses, and we take the argument of this. So one way we can do this is through minimum Bayes risk re-ranking. And so what we do is we create an n-best list, and then we create an error matrix and a probability vector, and we multiply these together to get the risk and find the element with the lowest risk. So to give an example, like I talked about before, let's say we only had these 4 hypotheses. We would create a matrix of size 4 by 4, where the diagonals would all be 0, presumably, because there's no error if you get the value correct, and then or exactly correct, and then element 1, 2 would be like the error of getting I don't know, given that the true answer was the second element here. And the 1, 2 would be the error of my name is Graham, given that the true answer was I don't know, et cetera, et cetera. And then by multiplying this matrix by the probability vector, basically each row in the resulting vector would be equal to this sum for one of the hypotheses, y tilde. So basically, this is a way that you can realize this in actual mathematics or code. So this is an interesting method. I think it's been underused in generation nowadays. So I would highly encourage you to know about it and think about it when you're building neural models for generation. Okay, so now I'm going to switch gears a little bit and to methods for improving diversity in n choices of outputs. And it's a little bit related to minimum base risk, but not extremely related. But anyway, entries in your n-best outputs can be useful to have basically an n-best list of outputs in cases where a generation model interfaces with a human user who wants to look at the outputs and maybe choose between them. So an example of this would be like auto reply for email, for example, which is trained using a sequence model. And then let's say you're giving a 3 best list of outputs and you want to provide the user with 3 different outputs that are plausible but semantically different so they can choose between them and get the best one. So however, entries in the beam can be very similar. So you might get no, nope, not at all, or something, in which case you're not really giving the user the ability to answer yes or I don't know or something like this. So basically, there are a lot of different ways to improve the diversity in top n choices. And one way to do this is to basically have a search algorithm like diverse beam search, which unfortunately I don't have a reference on the slide, but feel free to ask if you'd like a reference. To basically encourage beam entries that are less similar to the others. So you basically upweight beam entries that are less similar to the other entries in the beam. Another method for getting more diverse responses is specifically applied to dialogue systems, for example, is to score using the conditional probabilities of the output, upweighting the conditional probabilities of the output, and then downweighting the unconditional probability of the output. So to give an example, the answer I don't know is a very frequent answer regardless of what the query is. And so because of this, its language model probability would be very high, presumably higher than the conditional probability, whereas my name is Graham or my name is anything would have a high conditional probability, but only in particular contexts. So it's like unconditional language model probability would be low. So basically by downweighting things that have a high unconditional language model probability, you would penalize I don't know and not penalize these my name is things. So that would help encourage the diversity in the outputs overall. So another thing that is worth mentioning is when we're doing ancestral sampling and we want to get outputs, if there's certain outputs that just legitimately have a very high probability, like 70% or something like that, if we sample an n-best list with regular ancestral sampling, we will get 70% of these outputs, basically. And this is good if we want to observe the probability distribution and look and say, oh, most of this n-best list is this particular answer. But this is bad if we want to, for example, get a more diverse look at the outputs that the model thinks is plausible, or even train models that use these sampled outputs, because more diverse would give you more training signal. So I won't go into the details, but basically what you can know is there are methods for sampling outputs without replacement. So what this means is sampling according to the probability distribution, but sampling according to the probability distribution like you omitted the each sample that you got when you sampled the next one. So if that's the case, let's say you sample I don't know first, you would never sample I don't know again, and you would be forced to sample other things for your later samples. Okay, so this was about diversity and other things like this. So now I'm going to talk a little bit about heuristic modifications to model score to fix some errors in, to fix some problems in search algorithms, like I mentioned before. So a typical model error is length bias, and in many tasks such as MT, the output sequences will be of variable length, but maximum likelihood training plus local normalization results in a gradually decreasing probability as you output more outputs. And this can result in the model's score favoring shorter sentences. And so there was actually a very good example of this right at the beginning of the presentation here, where you notice that the empty sequence, despite the fact that it had a lower score than either A or B at the beginning of the sentence, actually ended up getting a higher score than another plausible output, simply because this output has three tokens, B, B, S, and you have to add the probability, the log probability of all of them together, whereas this one only has one token. And there's actually research that shows that essentially the empty sequence gets a higher probability in many cases than the best scoring non-empty sequence. So this is actually a fairly large problem as long as you're training models using the standard maximum likelihood objective. So one very common way of fixing this is normalizing by the length. So instead of calculating the log probability or doing search to maximize the log probability of the sequence itself, you divide by the length of the sequence to find the sequence that has the largest average log probability of each word of the sequence. And this is kind of the default now in many different, essentially, sequence modeling toolkits. There's also more complicated heuristics, like, I won't go into the details here, but basically these are heuristics that were used by the Google machine translation paper. Yeah, you can go crazy with the heuristics if you want, but basically the first one is commonly used, so it's definitely worth knowing about and knowing that you're using this. Nonetheless, these are heuristic methods, and they're not actually well connected to, for example, probabilistic models or anything like this. A better method, or more well-motivated method, is basically to predict the output length directly given the input lengths. And a very simple way to do this is to calculate the length of the output given the length of the input using corpus statistics. So you basically just count the number of length 25 sentences given the input was length 20, and use this as the probability of the length of the output. And you can then add this in to the overall score. And this is a very simple method, nonetheless quite well-founded, and it's guaranteed to bias the model towards the distribution of lengths that you actually expect given the input. So I would recommend considering this if you are having length problems in your model. Finally, I'd like to talk about search algorithms that kind of are intentionally hobbled. They intentionally are made to make errors, um, and that improves the perceived accuracy of the models. So if we remember, a limited beam search can help. So you could actually tune the size of your beam search to get the maximally effective search algorithm. And notice the light green one here is actually using normalized beam search. So even with normalized beam search, you still end up having these problems here. So basically this turns the size of beam search into a hyperparameter that you could be using. So another variety is top K sampling, where it's basically like beam search with histogram pruning, but instead of doing this, instead of doing beam search, you're doing sampling from the top K example. So you basically filter out really like all but the 16 most probable ones and generate an output randomly. And then there's nucleus sampling, which is like beam search with probability mass pruning, but you sample from the remaining hypotheses. So you basically sample from the top outputs that have a probability of 0.95 or higher. So both of these are kind of like a mix of beam search and sampling. So these are another way to do things. I would like to caution about the use of these sampling-based search algorithms. And the reason why is sampling necessary for diversity? This is questionable. We could use diverse beam search instead. In addition, results are inconsistent from run to run. So you need to consider the variance from this in reporting or debugging your models. So this is in addition to variance in training and data selection. So if you're generating outputs using sampling, you should also generate the span of potential, accuracy scores that you could get from different runs. And another issue is that it conflates model errors and search errors. So if you make a better model that suddenly does, better at modeling, you might still get worse results because the search algorithm that you're using, like sampling, cannot find the output that your model likes. So beam search is actually usually finding, when done appropriately, usually finds outputs that have higher model score. But you might not be able to find these when you create a better algorithm, training algorithm. So finally, I'd like to talk a little bit about search and training. So there's a couple methods to use search and training directly. And so basically, beam search has its own issues. So we've talked about exposure bias before. And there's also label bias due to scores being locally normalized and having to kind of filter based on these locally normalized scores. So this method of beam search optimization, basically what it does is it trains a model with beam search and it tries to optimize the beam search algorithm or the beam search procedure so that the model makes fewer search errors. So you basically run a beam search until the model has a search error. So this example here is demonstrating that the word runs falls off the beam. And when runs falls off the beam, we know we'll no longer be able to find the best output because it would be pruned away according to beam search. So what this does is it then puts the next best score back onto the beam, and then when it falls off the beam again, it records when it fell off the beam. So then we create a contrastive training pairs where it says a red dog runs quickly today is our gold standard hypothesis, and then blue dog barks is kind of like a negative hypothesis that we want to downweight, and home today is a negative hypothesis that we also want to downweight. So basically what it's doing is it's scoring, it's upweighting the the gold standard and downweighting the things that cause the gold standard to not be the gold standard output, essentially. This can also be turned into a differentiable procedure. So basically, this is a paper that I did together with Kartik Goyal and others at CMU. And basically, the way this works is it's kind of like beam search optimization, except each of the things in beam search is a differentiable procedure. And so instead of taking an argmax like we have to do in beam search, we have a continuous argmax. And I think this model is kind of neat because this method is kind of neat because it demonstrates how you can essentially do backprop through kind of complicated search procedures. So you might want to take a look if that sounds interesting to you. And finally, an important other thing to know about is actor-critic. So actor-critic is basically the learning version of future cost. So if you remember, the future cost is basically where we have a model that predicts how much extra penalty we'll have to pay to get to the end of the sentence. And what actor-critic does is the neural model is an actor that predicts actions, like actions over the next word. And then we have a critic to predict the final word, the final reward, which would be blue score for, like, for example, an MT model. And then the actor is trained similarly to the reinforce algorithm, where the critic is trained with actual results of the final score. And then we use both in the search procedure to find the best output at test time. Okay, so that is all I have for today. This was probably a lot of content, but hopefully it was clear and interesting. So from this, I would like to talk a little bit about the structured prediction problems that you're interested in for your work, and think about what search procedure are you using? What are the types of search errors that you might be encountering? And if any of the methods here could potentially be applicable to fixing these search errors. And if you have a moment, you might even output in NBest with a smaller or larger beam size and see if any of the things in the NBest list are better than the top one that your model was able to discover. So thanks a lot, and that's all I have for today.